Hello student, welcome to today's session. So I wrote categorically this video is for whom? Who all who all would get benefited from this content of this video is a very important question to address with, because this particular video would go in length. So those of you who have done whole of your organic chemistry and are not feeling confident about the organic while solving the problem that you don't feel confident about, so this video is for them. Or for those who are feeling quite confident because they have done lot of good questions and now want to take some challenge questions, this video is for them. So it is going to cater both those who are feeling underconfident and those of you who are feeling overconfident. So use if in case you like this particular content of this video, do use this hashtag as much as you can wherever you are studying. So let's go directly into the problem solving. So I'm saying you would be going to see 10 questions, and through these 10 questions you are going to revise whole of your organic chemistry. So these are some of the questions are quite challenging, quite interesting in a way that you feel quite strengthened with the entire syllabi of organic chemistry once you are done with this particular discussion. So here comes the first question. So hydrolysis of A to B, the fellow is saying that reactant and product both are given to you, and you are supposed to tell the mechanistic viewpoint adopted during this reaction. So the beauty of the organic questions are that at times, as a student, if I would see that is this question comes from the amine chapter or from the carboxylic acids or from the phenols. This is the quite interesting one, which way it is to be addressed with. So if you are not very clear with the discussion, if you are not clear with the entire syllabi, you get entangled with this particular question. So the examiner is asking that A undergoes tautomerism, then hydrolysis, then undergo decarbonylation, and somewhere also they have wrote tautomerism, hydrolysis, and decarboxylation. So let us go into the details of this particular question, that how we can address this particular question. So here you need to see into the fact that what basically we can go with, that what are the things given to us. First you have to see you are being given amine, and amine is to be treated with water, and what first thing we can think about is that it would undergo a sort of tautomerism. So this bond goes here and this goes here. Is it okay? So if in case I do so, so here I would get NH, and this carbon would get a negative charge, and that would, this H positive attaches to this. So H goes here. Similarly, you can do the tautomerism from this side also in the similar way, as well as you can do the tautomerism from this side also. So once you do the tautomerism, you happen to get on all the sides imine. This is particular compound is called as imine. So this is first viewpoint here happened as tautomerism. If you are not clear with, because many of the students only remember the keto-enol tautomerism. So now what next we can think about, because now you can see this, I have talked about this particular reaction many times in other videos also, that if you have ever got imine in front of you, just see it, this NH group is 7 plus 1 atomic number of electrons are 8, and here also it is 8. So you can easily swap NH with O group, provided you have to strongly heat it, because the refluxing is required in this case. So what basically is the viewpoint here is, first the lone pair is being attacked by H positive, and you happen to get something like this NH, nitrogen would get a positive charge. Now this is what you call it as simple resonance. This we have done in many times in other videos also. So here you would get a positive charge on a carbonyl carbon, then water's lone pair attacks it, and this happens to give you RCH, and here the oxygen now would get a positive charge and NH2. And now lastly you would do the intramolecular proton exchange, because still you have a lone pair intact here. So you end up getting here you would get OH, and here you get NH3 positive. Now if you would strongly heat it, this is the step of great importance, this last step, because Now this underwent this ammonia goes out and leaving behind you the ketone. So you converted NH group, CHimene got converted to aldehyde on adding water in presence of H positive. So it's the same viewpoint we can take it here also, that here it got converted into CO. All of these got converted. Beautiful question it is. All of these got converted into CO. Now thereafter, they said that thereafter what we can think about is that if now you could carefully see, this is a case of alpha beta. This is a beta keto acid. For this also, lot of videos I have made on to the topic of decarboxylation. You can refer to that. Beta keto acid, whenever you have any compound of the type beta keto acid, something like this, if you have ever seen this site of a compound, that if you have this is alpha beta, so beta keto acid easily undergo decarboxylation on heating. So the point here is this goes here, this goes here, and this goes here, and as a consequence of that you end up getting something of the type enol of this type of thing is being generated, and ultimately this changes to ketone. So what I'm trying to say here is that basically it is a case of beta keto acid, and beta keto acid, if is being heated, this carbon dioxide goes out, leaving behind a tri-keto compound, which easily now again would undergo tautomerism. Because why the tautomerism is taking place here? To retain again back the aromatic character. So the H from here and one of the H from all of these would undergo tautomerism. So once they undergo tautomerism, this goes here, and similarly if I would take this one, this goes here, and this way we happen to get with the final product which we were looking for. So you end up getting a double bond here, and a double bond here. So you would get the compound which they are asking for. So basically what we can think about here is what are the steps we have taken care of. Here first step we end up getting tautomerism, if I would say. Then this may be said as to be, or rather I would say this as to be hydrolysis. The second step is hydrolysis. Then the third step is decarboxylation, and the fourth step is tautomerism. So these are the 3-4 steps which we have taken going from starting material to the final product. Beautiful question it is. So let us see what they have suggested us. So I could see that tautomerism happened, then hydrolysis, then decarboxylation to give the B. So after decarboxylation, they haven't wrote in any of the 4 option anything about the tautomerism. So the answer to this question would be C option. Beautiful question, which in a way strengthen many things. During this discussion we get to know that if in case you are being given this sort of a starting material, how to go for it. First the tautomerism I did, then and similarly we went on going from A to B site. Okay, so coming on to the next question, this again is a very interesting question which you have to see it and check it out, that if you can do it by pausing the video. So in this question what you could see is that you are being treated with potassium amide and a starting material is given to you. Now the point here is amide is a very strong base. This is the first thing which you keep in your mind, that amide is a strong base. It's a strong base as well as it's a strong nucleophile as well. But as a matter of fact, here you could see there is an acidic hydrogen available to me. This is the acidic hydrogen. So one way is that I just would bring amide ion and would abstract this H positive. But if in case I do so, what I would end up getting here is something negative charge here and CO, and this negative charge is also resonance stabilized due to the presence of carbonyl group. It got resonance stabilized also. Now the point here is this is what you have to see. Again I am saying you would not get to know in the final paper that the question is coming from, is this question is from amide, is it from the chlorobenzene, or is it from something else. That you have to figure it out, and you have to keep your options open, because in the paper, as I said, that in organic chemistry, you always have to read the mind of the teacher, that examiner, that what he want, how the reaction to be driven towards. Now the point here is that what basically you are being given with is the starting material. Amide is a strong base, you abstracted this and you would get the negative charge. Thereafter, what you can think of, that which way it should go. This negative charge can come onto this oxygen. In that case, what you end up getting here is something of this type. You would get N double bond CO negative, and you would get something like this. Or now the point here is that what you can think about is, in this case, that one way is that if in case you think it like this, that because you have to select out of the 4 options available, so the 4 options available, one may go it like this way also, that this negative charge may, although chlorobenzene, because there is a partial double bond character, this would not be a good site for nucleophilic substitution reaction. But I may think of this way, that if it would attack it like this, what answer do I get here? So I would get something of this type. Now the beauty of the question is, as we proceed, you get to know that why is it beautiful question. So you would get this sort of a question. One way is think. So one line of thought is this way. One line of thought is this way. Another line of thought you can think about is that if I just, so here I started with the most acidic one. Another way is that if I would abstract this one, because soda amide, potassium amide in the presence of ammonia is also a requirement for a reaction to go through benzene mechanism. So if I would abstract this H positive out, this bond goes here and Cl will go out. As a consequence, what you happen to get here is, just hold on, let me add one page here. Just hold on. Okay. So if I just would add one page here to make the things more clearer to you. So what basically do I get here? So one way is that, as I said, that there is a chlorine here and you have NH and CO along with a phenyl group, and I just have abstracted this H positive. So if I just would abstract this H positive with amide, and here I would get a benzene. So what next do I get here? So NH2 negative has abstracted the H positive. So ammonia went out, and another way to discuss the same question is something like this. So you would get NH, CO and pH. This is the another way to think about the same thing. Now the point here is, what next? Because benzene is never a stable, it's an intermediate which has to now again get the aromatic character back. Although it is again the aromatic, but this triple bond is to be removed with. So I can do it like this. This lone pair goes here, and if I would attack this one and this bond goes here, so the next step which I would get here is something of this region. So oxygen comes here, NH, this would get a positive charge, and CO, and along with here you would get a pH and a double bond. Now the point here is, we almost have reached the point. Now the last step is intramolecular proton exchange. So the last step which we get along with is intramolecular proton exchange. This H positive would come to this side and ultimately give you the same product. Now here the question has asked in a simple way, that the examiner is just checking us that what product do we get in this particular reaction. So the product which we get from here, as well as thinking from this line of thought, this also gives me the same product. The product is same. So how this question would have become very interesting, that which way the reaction might have proceeded. So I would have taken it through the benzene mechanism. Why? Because chlorobenzene, if has to undergo in the presence of soda amide or potassium amide, it adopts instead of AR-SN2, aromatic nucleophilic substitution reaction, it happens to go with the benzene mechanism. So the question was interesting if the examiner would have asked something more about the question. So here the answer to this question shall be C option. Other options can be discarded very easily. So here the point of discussion is that which way the reaction might have gone. Is it through AR-SN2 or benzene mechanism? So this again is a very interesting question. The answer to this question would be a C option. Coming on to the next question. So in this question, what basically is being asked is, you are being given a activated methylene compound. This is a activated methylene because here you have a CH2 and that CH2 is attached to two CO groups. So it is an activated methylene group which is to be treated with this. Again is a very beautiful compound. So from the chemical bonding point of view, this is C6N4. This again is a very, very interesting question. That C6N4, they can ask you in terms of bonding aspect, and I just would give you one homework as well, that just tell me if you could make C6N6 in such a way that it would retain the aromatic character. So if you could share it with me, the IUPAC name or something like that, it's a very interesting question. That C6N6, can we make it in any sort of aromatic compound? Anyhow, so in this question, again, you are being given some options. So here you need to be very vigilant about that the starting material is given OH negative. They are asking us about the product P, what is P in this reaction, and this is the side product they have thrown out. So this would also give us many ideas about how the reaction would have proceeded. So this is very normal to explain here is that when you are being given, let's say, let me start the question. So in this question, the OH negative is being given to you, and now OH negative as a nucleophile can attack this carbon and could go like this, or OH negative can attack this position, go it like this, or OH negative just would abstract the H positive. Here if it abstract the H positive, it's a base, and here if it is attacking, this is attacking as a nucleophile. Now here the point is which way you have to take the reaction, because in the reaction we could see that there is a attachment. These two bonds, these two entities, these two starting material got attached somewhere and thrown out some leaving group in the terms of this one. So that in a way shows me that the first step they just have taken in terms of acid base reaction, because activated methylene is quite acidic, which is having a pK range between 9 to 11. Any activated methylene is having a pK range of this one, and definitely it is going to happen in a acid base reaction. So what one thing we can think about is that, because in that sense, if I just would generate a carbanion, which this carbanion is also very stable because it is resonance stabilized on both sides, and this carbanion now could be acting as a site of attack as a nucleophile to attack onto this CN or to this C double bond C. This is a better way to view the question. So let us see if we could get something. So first H positive gone out with the water and you just have generated a carbanion. So what I can think here is that this CH negative then could attack this carbon, because it is almost non-polar, although CN is an electron withdrawing group, but there is no polarity as such, and this way it can go it like this. If I do so, what I can think here is this is a negative charge, and if I just would play here that this negative charge is quite resonance stabilized because of the fact that there are two electron withdrawing groups, this can easily stabilize it. It can easily stabilize it. So this is a good viewpoint to go with. So this way we can go it like this, and the water which gone out, now same water would give it H positive to the negative side, and you end up getting something of this nature. So you end up getting something of this nature. So here you would get CN, and here you would get CH. And how do you get this CH? This is very important. This H we have taken from the water, and OH negative went out again because it is used in a catalytic amount. Now what next we can think about? Again, this OH negative can abstract this H positive because this is activated methylene, and these CN groups would increase the acidity further. So as a consequence, because the side product which they have shown is actually the viewpoint which is driving me towards this direction. So the next step we can think about is, here you would get a negative charge, and here you have CN, and this is CH, CN. Okay, so next step we can think about is, if I just would create a double bond here and throws this out, because if I throw this out, I would get the product which they are trying to show it to me that this is the product they are looking for. They have generated a double bond between the carbon-carbon containing the CN. And along with it, what you would get is CH negative, CN. And this negative is again resonance stabilized, because negative charge can go on both of these CN, because CN is having a triple bond, so it can easily stabilize this carbanion. So this carbanion again got stabilized on to the both sides, and the H positive which we have taken out with the water, the same water would give the H positive to this, and we would end up getting CH2CnCn along with OH negative. So the three things which we get here is, one is this product, along with the OH negative is used in a catalytic amount, and this CH2CN2 has gone out of the system. So this is again a very beautiful question, which you have to, if you would do the practice, you would get to know what answer do we get in this particular case. So what major inference we get from here is, from this particular leaving group, the leaving group which has gone out, that actually drove me towards the answer D. Answer D would be the right answer to this particular question. Again, it's a very important question. Okay, so the next one is, which of the following statement is correct? Although it seems like easy sort of a question, but I would rate this question again to be very, very important from the nitrogen containing compounds. So they are talking about something in regard to methyl isocyanate. Methyl isocyanate, they are looking for the hydrolysis of methyl isocyanate. So let's see first what methyl isocyanate look like. So methyl isocyanate is if I would go with the chemical bonding aspect of it, so it is having, nitrogen is having 5 electrons, and these are the electrons of the carbon. As a consequence, we happen to say it like this, that here the nitrogen is having positive and carbon is having negative charge. So what I am trying to say here is that methyl isocyanate in methyl, from the chemical bonding aspect, if I would show it like this, this is having a coordinate bond of this nature. So the point here is that carbon is having a negative charge and nitrogen is having a positive charge. So make it a point, this is a categorical statement which I am going to speak it here, that isocyanates are the class of compounds in which the addition happens, the addition of a electrophile nucleophile happens onto the same carbon, unlike any other starting material. If you have a double bond of a carbon-carbon, if H positive goes here, then the Cl negative goes here. But if you have a carbonyl groups of this type, say for example, if H positive goes here, then the Cn negative goes here. So during any addition reaction, electrophile and nucleophile add across to the double bond, depending on the nature of the double bond, which way it has to go, which way the H positive and Cl negative or H positive or nucleophile has to attack. But isocyanates are the class of compounds in which both electrophile and nucleophile add across to the same carbon. What I am trying to say here is, if the electrophile comes in its vicinity, this would get attacked like this. Now here is the problem which many of students do it in a wrong way. So electrophile got added here, and now if I have to add the nucleophile again attacks onto this carbon and opens it like this. So this is very, very beautiful and very interesting to see that electrophile and nucleophile both add across to the same carbon in the case of isocyanate. What I am trying to say here, that at times you would feel that this nitrogen is having a positive charge and this is having a negative charge. Now what basically we have to do, hydrolysis. Now which hydrolysis it has to go? So they will give you like this, water in presence of H positive and water in presence of OH negative. So this hydrolysis would never happen, this would happen. Why is it so? Now at times you would take it like this, that first let me show the H positive, acidic hydrolysis. So H positive goes here. Now thereafter what would happen? So this would get a positive charge is still there, but here you would get H positive. So the H positive's charge got omitted. So now what basically second step has to go with? Lone pair of water. So water's lone pair would not be attacked here because nitrogen is already has its octet complete. So it would not have the any tendency to gain the electrons because its octet is already complete. It cannot make 5 bonds. But yes, this carbon can be attacked and this bond opens like this. As a consequence, what next structure you would get here is nitrogen's positive charge got emitted and the positive charge came onto the oxygen. This is the thing which we get. Next step what we can think about is that there could be intramolecular proton exchange, or simply H positive has been lost from here and you would get a compound of the type this way, CH3 and double bond CHOH. Now this can undergo tautomerism. So the tautomerism, it would be like this, and basically this H positive went to this side. So basically you end up getting NHC double bond OH. But the reaction doesn't stop here, because still you have H positive with you. So the H positive again would attack this lone pair, or you can take it like this also. The lone pair got attacked, or whichever way you think about, because both ways it is resonance stabilized, and the negative charge can come here also. So the next step which you would get here is NHCOOH. H positive again attacks onto the carbon of the carbonyl group, and now what next you can think about. So here you would get a positive charge onto the oxygen, and the lone pair goes here and this bond opens it like this. This is nothing but a resonating structure, and you would get something of this nature. Okay, and positive charge comes onto this, and now water again attacks onto this carbon and this bond opens up like this. You can think it like this also. So CH3NH, and again you would get OH, and this would get a positive charge H and OH. Now again the intramolecular proton exchange would happen to this side, and ultimately what you happen to get here in this case is CH3NH positive, so NH2 positive along with OH, H and OH. Ultimately this bond goes here, this opens up, and what you end up getting is CH3NH2 along with formic acid, along with a molecule of formic acid, H positive gone out as such. So basically what you happen to get here in this case is, if you ever would get methyl isocyanate treated with 2 moles of water in the presence of H positive, you end up getting primary amine, methylamine along with formic acid. But this hydrolysis would happen only in the acidic medium. I already have explained why it would not happen in the basic medium, because in the basic medium, although it seems like that it could happen because you are adding OH negative in the presence of water, OH negative cannot attack this carbon. This is the point which you always have to remember. This possibility is not possible, because nitrogen's octet is already complete. It is having no tendency to accept the negative charge of OH. So this is quite a important question which you always have to remember, that isocyanates are the class of compounds in which the addition happens across the same carbon. Electrophile, nucleophile add across to the same carbon. That is very important. So basic hydrolysis would not happen. Acidic hydrolysis of methyl isocyanate gives formic acid. This seems like a correct. Let me check the other options. Acidic and basic hydrolysis, no, basic would not happen. Complete acidic hydrolysis, this is very challenging question now. Complete acidic hydrolysis of methyl isocyanate gives N-methyl formamide. This in a way is a right statement, but not the complete hydrolysis. That was the partial hydrolysis when you added 1 mole of water. Let me show it to you once again. So you could see that here I have added 1 water molecule. This is the first water molecule which I have added. When I added the first water molecule, what I ended up getting here, I just have got where I was. Yes, here it is. On addition of 1 mole of water molecule, I happen to get N-methyl formamide. N-methyl formamide. And another water molecule I have added here. That is the second water molecule. When you added the second water molecule, that means it's a complete hydrolysis. So partial hydrolysis may, if they have given it here as a partial hydrolysis, then I would have said as N-methyl formamide is a right statement, but they have said complete hydrolysis, then in a way it becomes a wrong statement. The best out of the 4 options then would become the B option. Again, a beautiful question it had been. Okay, so the next question, what is coming in front of us? Which of the following reactions may be said as brominative decarboxylation? Beautiful question. Brominative decarboxylation. What do we mean by brominative decarboxylation? Brominative decarboxylation means that during the reaction, as a starting material, you are adding bromine into the reaction, and along with there is a loss of carbon dioxide. Decarboxylation means loss of carbon dioxide. So this is the first reaction, which is very popular one, is Borodin-Hunsdacker reaction. If you could remember, Hunsdacker reaction, which we happen to see, Borodin-Hunsdacker reaction is a reaction which we happen to see in the preparation of bromoalkanes or bromobenzene. So here the starting material is silver salt of carboxylic acid is being treated with bromine. So AgBr goes out along with the carbon dioxide, and you end up getting bromobenzene. So we may say it has to be bromonative decarboxylation. So this is the right statement. Why is it a right statement? As I just have explained, because you have added bromine and there is a loss of carbon dioxide. Now let me go into the second option. Second option is salicylic acid, if you could recall. So the first option we have already discussed. This is Borodin-Hunsdacker reaction, where we just have shown it like this. AgBr goes out, and this happens to adopt the free radical mechanism, which we will do somewhere some other day. So this is RBr you are going to get. This is the another one which is a very, very important one. So make it a point, this can come in the JEE mains or NEET examination very soon, in this year only. Quite an important question it is. So here bromine is being added and you have to heat it. So what would happen? This carbon dioxide would first go out. First, remember it like this. Carbon dioxide would go out, but the reaction doesn't stop here, because it is a EAS, electrophilic aromatic substitution of phenol with bromine. So ultimately you end up getting white precipitates of bromine like this. And this is very, very important to remember, that brominative decarboxylation may happen if the OH ortho to OH group is having COH group or sulfonic acid group. Just like if you have same answer you would get if you have a sulfonic acid ortho to this position and you are adding bromine, ultimately you end up getting the white precipitate of this compound. So the mechanism of this reaction is a very interesting and important one, which we will do some other day. But here you have to remember it. These are the two reactions which may come in the paper, which is quite an important one. Let me give you a little glimpse of it, what basically is happening here. So you know that OH is a strong orthopara directing group. So this bond goes here, and this is delta positive, this is delta negative. The pi bond comes here. As a consequence, what you would get here is a double bond. Here you get a positive charge. This is already there in the system, and here you would get bromine along with minus Br negative. Br negative went out of the system. So what basically you now get with, this is the entity which you would get with. And now what would happen, because carbon dioxide can go out of the system to generate back the aromatic character, and wherever any gas goes out of the system as a leaving group, that reaction is quite forward driven, because whenever any gas is coming out of the system, the entropy of the reaction becomes very high and the reaction got driven to the forward direction. So once you get the phenol, bromophenol, orthobromophenol, the reaction doesn't stop here. Another 2 moles of bromine is again required to do the EAS reaction further, and ultimately you would get with the, I just have given you just a glimpse of the idea that how it is to be taken care with. So here you would get white precipitate. Since you are getting white precipitate and precipitate separates out as a solid, so again this reaction got driven to the forward direction. So that also is a very important viewpoint to keep in mind. So what answer do we get for that question, by the way? So A and B could be said as brominative decarboxylation. This would not be, because you just have double bond. Across the double bond, if you just would add bromine, so bromine would add across to the double bond, and it would not result in decarboxylation, because the bromine is just being added across to the double bond. Simple addition reaction of halogen across double bond. So the best answer for this is D option. So the D would be the right answer, because they said both A and B are brominative decarboxylation. Adding bromine and removing the carbon dioxide. Again, very important question. Okay, so the next one, it is quite draining. We happen to reach on to the 6th question. Identify the final product among the following. This again is a very important, seems like very important question. So you are being given a ketone which is being first treated with bromine in presence of acetic acid, followed by pyridine, ozonolysis, and then OH negative and heating. So this again, in a way, in one question, everything in regard to the aldehydes and ketones is being checked with. So let us do this question. What do you think is the first viewpoint, first line of action in this particular question? So what I'm thinking of is the first case which we can think about in this particular reaction is alpha halogenation. In acidic medium, there is a high chances of doing alpha halogenation. So what basically happens is there is a lone pair here, and this lone pair is going to be get attacked by the H positive. As a consequence, you would get a positive charge here, and this opens up like this, and this in a way then would lead to tautomerism. This would get OH, and here you would get a positive charge, and here you have a alpha hydrogen. This is the alpha hydrogen which we can think about, and this goes here, and this lead to a formation of a double bond. So basically what I did is a sort of tautomerism I happen to did here at the first go. So first you would get a tautomeric form of this compound. Once you get in the acidic medium, which all of you people know it, that in the acidic medium or in the basic medium, tautomerism get enhanced with that. Keto tend to go into the enolic form when any catalytic amount of acid or base is being added with. So thereafter what we can think about is the next step. What we can think here is that once you get this entity, here you get the OH double bond, and now this bromine can be attacked by the viewpoint of this lone pair goes here, this attacks here, and this goes out. As a consequence, what you would get here is a type of a product which I was referring to as alpha halogenated product. And lastly, what would happen is this Br negative went out along with this H positive. So first entity which you would get here is with alpha brominated compound. So this is what you would achieve in the first step. So once you get the first step done with, now the next step they have said is heating it with pyridine. Now this basically is a alpha halo ketone. Alpha halo ketone is a very good site to do with E2 elimination. That elimination which happens in a concerted manner, where bond breaking and taking place simultaneously, because this bromine can easily be thrown out with the help of the pyridine. Pyridine is a strong base or relatively good base. Pyridine is what? C5NH5N, or in other words I can show it like this also. This is what you call it as pyridine. This compound is pyridine. So pyridine abstract this H positive, this bond goes here, and bromine goes out. As a consequence, you would get a compound of the type alpha beta unsaturated ketone. Alpha beta unsaturated ketone is going to get with. Now thereafter what they have wrote, so we reached to this point, then they did to do it as a ozonolysis. Now all of you might be knowing that in the ozonolysis, the tip to remember here is this is a case of which they have given is a reductive ozonolysis. That you have to treat it with ozone in the presence of zinc. First, the tip to remember is whenever you have to do the reductive ozonolysis, wherever there is a double bond, just break it from the center and place two carbonyl or oxygen groups on both sides. First, remember this tip 2. So you end up getting this. Here also you would get the same compound. So you have to place, let me write it once more for you. What I just have done is that wherever you are supposed to do the reductive ozonolysis, you have to break the double bond from the center, and you have simply to place two oxygen in between. So basically this is aldehyde. This also in this particular case have generated a aldehyde. So basically if I would go dig deep into this, because then it would take a good amount of time. Basically what I just have said it to you, First, on addition of ozone, there is a proper mechanism for which I would make a video later on. A ozonate is being generated from the alkene like this. So this is called as ozonate, and this ozonate can now further go in two ways. One, we call it as reductive ozonolysis, and second, we take this as through oxidative ozonolysis. There are two ways to go with. In this particular case, they have shown about the zinc only. So what basically you have to do here is, you have to break it like this. You just would open it like this, and what basically you would get a ketone or CO group generated in between. And if it is being done with zinc, so zinc oxide gone out with this oxygen taken out, this zinc has taken this oxygen out. So this is a case of reductive ozonolysis. One way is of thinking it like this. What to be seen in the case of oxidative, that also I will explain. Just hold on. So what basically the tip to remember is, if in case you are being given a reductive ozonolysis, first you would going to add the ozone. In the second step, any of these 3, 4, 5 reagents can be used. Zinc, hydrogen in the presence of nickel, or dimethyl sulfide, or triphenyl phosphine. Any of these can be used. So basically, wherever you have a double bond, you just have to generate a oxygen. Reductive ozonolysis is easy to remember. So you would end up getting this type of a thing, because in this case, from the ozonate, they will throw it out zinc oxide or water or dimethyl sulfoxide or triphenyl phosphine oxide. So these can come out, just like in the previous case I have shown that how zinc abstract the oxygen from the ozonate. So these entities also would abstract the oxygen, and that's why it is called as reductive ozonolysis. But in the case of oxidative ozonolysis, in the first step you are going to add the ozone. In the second step you would not be adding the zinc. In fact, you are going to add some oxidizing agent. Any of these oxidizing agent is added. What is the tip to remember? That wherever you have double bond CH2, that, or wherever you have received aldehyde in the reductive ozonolysis, that will change into acid. If it is formaldehyde, it will become formic acid. If it is some aldehyde, it will change into corresponding carboxylic acid. But ketone would remain as such. Ketone would not be oxidized during the oxidative ozonolysis. The tip to remember is, during the oxidative ozonolysis, what product do you get? Whatever product you have achieved through the reductive ozonolysis as aldehydes, those aldehydes would change into carboxylic acid. Ketone in the reductive and oxidative would remain as such. So a question went in a length. So this is the thing which we have received. Alpha beta unsaturated ketone, which is to be ozonolized. So you would get this thing. Now again becomes a very interesting question, that this is now it is to be treated with OH negative. So this is taking us towards the fact, do I go through the Cannizzaro reaction or aldol condensation, or intramolecular aldol or intramolecular Cannizzaro? So that would depend how the products are being aligned in the options. So what first I can think here is that this particular part did not have any alpha hydrogen. So this is a site of attack for a reaction to go towards what you call it as Cannizzaro reaction. But here you would see a alpha carbon or alpha hydrogens are available. So this is a site of attack of deprotonation. And if I do so, if I would abstract one H positive from here, so you would get this carbon ion. Now the point here is, I am just ignoring the Cannizzaro because in the product there is cyclization happened. And we will come back onto the question why I have ignored the Cannizzaro. Now the point here is that you have generated a carbon ion. Now this carbon ion again is a very interesting way to explain that it can attack this one. One way of thought is this, or other way of thought can be it can attack this one, because this also has delta positive, delta negative. This also has delta positive, delta negative. But I would go with the pink marker. Why? Because the aldehydic part is more electrophilic carbon as compared to the ketone. And ketone is having a sort of, because it is being attached with the benzene part, so it is also got resonance taking place here, so which would decrease the positive charge onto the carbonyl carbon. So I just would go with this point, that aldehyde. Or second thing also is there, if I would attack with the green marker, it would cyclize to give me 4-membered ring. With the pink marker, it is giving me 5-membered ring. So there are many things which are, endorsing me to go for this side. I would attack from this side. So if I would attack it from this side, what I would get here is something of this type. This CO would remain as such. This would become negative. And here this CH and this is CHO. This is what we received with, isn't it? And here I have taken out the water because during the aldol condensation, it is again base catalyzed. So whatever H positive came out, that H positive, that is what you call it as workup. So the H positive would come from the water and this H positive goes here. So we almost have reached the answer. So we have reached to this point. So this is being generated. Now this is to be heated. Once it is to be heated, because this H positive and this OH negative would go out. That is what you call it as aldol, and you end up getting a compound of this nature. Beautiful question it had been. It is taking into consideration many aspects. So this particular compound is quite stable as well, because the unsaturation which came, it is doing resonance on both sides. So that in a way shows a very interesting viewpoint here. Now, if I would have attacked it from this position, then the probable answer I would have received with of the nature, I would have got a answer of this nature. This would have CHO here and CHO here. And ultimately on heating, if I would have gone to this side, then I would have received this sort of a statement. This again is having a good one, but it is having a 4-membered ring, and there is a anti-aromatic character coming here, which in a way is telling me not to go with this way. And the carbonyl carbon of this carbon is having less positive charge as compared to this one. So many things are being discussed and many things are being channelized here. So this is the way it is to be interpreted. So let us see what options they have given. Let me go into the option area. What are the options given in this particular question? Okay, so I could see this option is being given to you, as well as this option is also being given. This is one of the things which is being made after ozonolysis. So that is there. So I think B would be the right answer for this particular question. Okay, moving ahead. So the video may go in length, but it is very interesting. Okay, this again is a very, very interesting question. So here what is being given? 2-methyl cyclohexanone and 3-methyl cyclohexanone is treated with aqueous NaOH. After some time, same compound is obtained. Same compound means whatever you started with, you get with the same thing. So this is 2-methyl cyclohexanone. So if you would treat it with OH negative, so this is the alpha hydrogen which can come out as water, and you would get a carbanion here. So when they have spoken about R, that means it's a pure enantiomer, because this particular entity, this is a pure enantiomer. In a way, I may say it like this, that this is having some pure enantiomer of this type, something like this, that it is pure because it is having its optical isomer, which would be S, because it is having a chiral center here. Now, what basically we could see here is that you would generate a negative charge here. First, I am not engaging the stereochemistry part, and then it can undergo, resonance to give you a compound of this nature. This is the negative part we have generated, and double bond and CH3. So what basically has happened here, if I just would see the representation of this particular sequence of things, this carbon was sp3. Now this carbon has become sp2. It has become sp2. So this is to be remembered with. This has become sp2. Now what went out is the H positive. H positive went out. Now if I just would add again the H positive, this H positive again goes back to that one, and now you would receive the same thing. Would you be receiving the same thing? Now it would undergo tautomerism. Now once it undergoes tautomerism, this H positive can come from the upper side as well as from the lower side of this planarity. This would come from the upper side as well as from the lower side of this planarity. So this H can make two things out of this. That this H can come like this, just like if I would show it like this. This H can come from the top side or it can come from the bottom side also. So in a way it will generate two things in a equal quantity. So what basically we are going to see here, this starting material was optically active because it would have some optical activity, some optical rotation, let it be plus a degree. It rotated the light by plus a degree, but it's, if in case I just keep it with the OH negative for some time, would not allow it to undergo any sort of condensation, and if I get back the same thing, that in a way would not be the same. It would have R along with S made here with, because you have got back the same thing due to the loss of the optical rotation got lost, because you would end up getting the resume mixture. So there would be a loss of optical activity happening in this particular case. But unlike in this case, here in case you have the chirality at the next carbon, which would not be engaged during the tautomerism, because if I just would abstract the H positive from here, so this part would, although this part would become just like with the many steps, I just would run down speedily, you would get the double bond here and this methyl would remain as such. If it is pointed upward, it is still pointed upward. And if you just would get back the same thing, because whether the H now would come from the upper side or from the lower side, it doesn't matter, because it is both would create CH2 only. So here you would get the H and here also you would get the H, and this part would remain same. What I'm trying to say here is that this part of the molecule is not engaged during the tautomerism, or this carbon is never went from sp3 to sp2 during the mechanistic viewpoint. But in the previous case here, in the previous case which we have shown it here, this carbon went from sp3 to sp2. That is why the problem came. So that is why the H negative could attack from upper side or lower, H positive could attack from upper side or lower side of that negatively charged species. So the point here is, what answer do we get here? So loss of optically activity in both? No, it would not be. Loss of optically activity in the former. Former is this one. So that is, and not in the later. So this seems like a correct one. Racemization in both? No, racemization would happen in the first case, because in that case an enantiomer has been formed. So enantiomer formation in the later, this is wrong. It is to be read in the reverse way. So the best out of the four option is the B option. So you could see that tautomerism along with isomerism of the type of optical activity got engaged with aldehydes and ketones in this way. So this interconnection of different aspects has to be understood while discussing the any problem of organic chemistry, and that in a way make the organic chemistry very, very interesting. Okay, moving on to the next one. Which among the following order of reactivity is incorrectly written? This is a bad habit of many of you people, that you don't underline the point whether they are asking correct or incorrect. So here SN1 always goes through the formation of carbocation. Wherever halogen is being attached, that is to be removed and you have to create a positive charge onto this. So what basically during the SN1 mechanism, first step is the formation of carbocation. So here simply you have to see which out of this carbocation is more stable. The one which is more stable, the reaction would go in that direction. So it got stabilized because of the lone pair of the oxygen, nitrogen here from the oxygen. So basically both are resonance stabilized, but I would keep this as to be more stable, the first one. Why? Simply because of the fact that nitrogen is less electronegative. So it has more tendency to give electrons to the positive charge, and once the positive charge came onto the nitrogen versus that onto the, if I would create a positive charge and a double bond and versus, so in a way this is again endorsing many things in the discussion. Both of these are quite a stable resonating structure. If somebody would ask you which out of this is more stable, I will say this is more stable. Out of these two, again this is more stable because the octet is complete. Although the electronegative element is carrying a positive charge, still the octet is complete. So both of these entities are more stable from the more stable than their respective carbocations. Second, now we have to see which out of 1 and 2 is more stable. I am saying 1 is more stable simply because nitrogen is less electronegative, carrying a positive charge, is more stable compared to the oxygen. When you are comparing, you have to compare it like this. So this is quite important. So obviously the SN1 reaction for this would be faster. So we have to pick the incorrect statement. So this in a way is a correct statement. So SN2 for this we have done in the earlier session somewhere also. If you could see into the SN1, SN2 discussion or SNI discussion in some of my DCD series. So here you have alpha bromo ketone. Alpha bromo ketone is a very good site for the attack of nucleophile. Why is it a very good site of attack of nucleophile? Because CO group is a electron withdrawing group, strongly electron withdrawing group, and this also would help when you have unsaturation at the next position to the carb. If I would say it like this, that there is a unsaturation here, there is also unsaturation here. Both of these unsaturations do stabilize the transition state. But CO being more electronegative or CO being more electron withdrawing group, it would enhance positive charge onto the first carbon carrying the halogen. So the attack would be faster. So this would in fact would go very fastly with the SN2. So this again would be a right statement. Next one is SN2 order we have to check with. This is primary alkyl halide. This is simple case. This also is a primary alkyl halide. Primary alkyl halides are the site of attack of SN2 because they always would, because SN2 is a concerted one where bond breaking making happens simultaneously. But it is primary, but the beta position, if I would say this has to be alpha, this beta position is sterically hindered. Because this beta position is having two methyl groups, which would create a steric hindrance. So the best way to answer this particular one is, because here alpha beta position did not have two alkyl groups. So here, because the backside attack has to happen from the back position or the rear side of the species. So if the rear side of species would create some steric hindrance, it would not be eagerly going through SN2. So among these two answers, I would say this is the better answer. SN2 would be faster for the first one rather than the second one. Okay, so here I would say the SN2 for this one is correct. This one also is correct. And what about the last one? So it seems like in this particular question, nothing is incorrect. So the question went wrong because SN1 they have asked. So I may say it like this. If I would do the thing, if this question would have shown it like this, then this would have been the right answer to this question. D would be the right answer to, oh sorry, I did the mistake. It was like this only. Okay, sorry. So here it was SN1. It is to be done. We would create a carbocation formation. So carbocation, the question was perfectly right. I just have overlooked it. So here you would get a carbocation of this type. So obviously the second carbocation is more stable, because you have to go by the SN1. So the carbocation got resonance stabilized from here as well as from here. Here you would get the resonance from one side only. So that is why we would be endorsing that the second substrate would be a better site for SN1 rather than SN2. The rate of SN2, SN1 would be speedier in the second substrate rather than the first in the D option. So we are supposed to tell the incorrect. So incorrect is D option. So D would be the right answer for this particular question. So two more question to go with. I am draining out. It is quite a lengthy question. Okay, the degree of unsaturation in the final product. So this again is a beautiful question to begin with. So first it is to be treated with alcoholic KCN. CN is a good nucleophile which can replace out the Cl negative. So what basically we can think about is, first step is that you have to take 2 moles of KCN. So this would attack this one, this position, as well as CN would attack this position. So this would lead to nucleophilic substitution reaction. As a consequence, you would get CN here, CN here. Now all of you might be knowing it, that wherever you ever would get the mechanistic viewpoint, we will do some other day. So if cyanide is, unlike isocyanates, cyanides can undergo both acidic and basic hydrolysis. This always, because we have already discussed in this video only that cyanides would undergo acidic as well as basic hydrolysis both, and they can can go partial hydrolysis and complete hydrolysis. So the matter of the fact here is that if cyanide is being treated with 2 moles of water in the acidic medium, you end up getting carboxylic acid with ammonium salt, and if you are treating it with 2 moles of water in the basic medium, you would get the carboxylate ion, because in the basic medium it would remain as carboxylate along with the ammonia. So this always you have to remember. So this is the case when you are doing it with the complete hydrolysis, and if you just would add 1 mole of water, then you would end up getting amide in this particular case. So this always you have to keep it in mind. So what they have treated with H3O positive, so you have to do the hydrolysis. So that means you would get carboxylic acid and carboxylic acid on both sides. Now the next step had been, if I would show you, we have reached to, so we did this one. Now this is to be heated. Now if it is to be heated, one more thing they must have added here, just to rule out any ambiguity. If I would write here is 2 equivalents, so you have added 2 equivalents of KCN, so that you just would throw out both the Cl out. Now this is to be heated. Now if it is to be heated, now this has came into a case of 1,7-dioic acid. For this also you just go through the decarboxylation video which we have done with you people in the DCD series. So you have 1,7-dioic acid, where I talked about Ohm's gap, if you could recall, oxalic, malonic, succinic, glutaric, and adipic, and palmitic acid. So all of these are 1, 2, 1, 3, 1, 4 effect of heating. So if you heat 1,7-dioic acid, what would happen? Dehydration. One is dehydration going to take place. Another thing which would happen is decarboxylation. 2 things would happen. Carbon dioxide would go out, and along with water. Now you have to be little vigilant about how you are going to join it. So 6th carbon is to be joined with the first one, or first is to be joined with the 6th one, or vice versa also. If you have taken out the carbon dioxide and water from the upper side, then 7th is to be if you have taken carbon dioxide from, then 2nd is to be joined with the 7th. So the point here is you may get a type of product of this type. Is it okay? So this is, you have to keep it in mind. So what next they have thought about? Let me show it to you. This is the product which we have treated with. Then it is to be treated with Grignard reagent. Grignard reagent is a site of attack for any sort of, because it's a source of carbanion which can attack the carbonyl carbon, followed by acidic hydrolysis. Would lead to alcohol. So what we are saying it in terms of acidic hydrolysis is, first you would get with O negative. Here you would get and followed by a counter ion is being treated as this one. When this is being treated with water in the presence of H positive, so O negative would abstract H positive, and hydroxy magnesium chloride, hydroxy magnesium bromide would go out of the system, and you end up getting alcohol. So basically this is the product. Or if in case you have joined the reverse way, then you would have got a ketone of this type. If you have the thing which I am saying it to you, that if you have taken out this as if I would show it to you like this, this is COH and this is COH, and if you have, I think we would get a different result in this case, that if water gone from here and carbon dioxide from here, then these two get joined with. In that case you would have achieved this product, and followed by RMGCl, RMGX or CH3MgCl, followed by hydrolysis. Then also, because here the examiner is asking you only the degree of unsaturation. So the degree of unsaturation in both the cases is 2. Degree of unsaturation is the sum of pi bonds and rings in a compound. So you just would see one ring here, one ring here. So basically you got 2 rings. So basically in this particular question, the degree of unsaturation happens to come out to be 2. But the products you can get with the 2 different products you can get with. And last but not the least, we have reached the 9th question, and now the last question. Find the value of X upon Y in the following reaction. So this again is a very beautiful question. Malaparide oxidation, the oxidation which we do with HiO4, in this particular discussion I have just made a video last week only, or 2-3 days back only, just refer to that one also. So when you have two OH groups adjacent and two CO groups adjacent, because they are saying, because they have shown you the final product, glyoxylic acid. Glyoxylic acid is this entity. This is what you call it as glyoxylic acid. And this is being received with, so what tip to remember we can take it here is that H and one oxygen which we get from HiO4, this is the shortcut which we have developed in that video also, and this would lead to the glycol splitting. So this bond got cleaved from here. So this carbon got a O, and you just have broken this, and this water went out. So here you have one H, so CH is retained. And what next you can think about is, so then what you can think here is another mole of, because I have to break it from here also. So this oxygen also came from the HiO4. So 2 moles of HiO4 is being used. So this OH and this OH, you have to take one water along with. So this OH got attached here, and one OH got attached onto this one. So what I'm trying to say here is that you end up getting OH on this side and this OH on this side, and this would change into CHO. So this is glyoxylic acid. So how many moles you used here is 2 moles of HiO4 has been used in this question. And I already have spoken of many things upon the malaparide oxidation. You just refer to that one, that the number of splitting or number of bond cleavages you are going to do during usage of periodic acid, that much number of HiO4 is being used. So I did 2 cleavages, so 2 moles of this is being used. And when you have to do the cleavage of adjacent CO groups, you have to take along with water also. Then only you can get the carboxylic acid. Another thing is HI. So in terms of HI, in the presence of red phosphorus, it is a very good reducing agent which happens to do reduction of many things, many of the oxygen containing compounds, just like alcohols. So here the tip to remember is that this oxygen and these 2 hydrogens would come out as water along with I2. This I2 would go out, and this H got attached to the R part itself. This would get attached to the R part itself. This H got attached to the R part itself. So RCH2H. So in another way I can say RCH3 along with the loss of water and iodine. But here you have 2 oxygen molecules in the carboxylic acid. So here you can take out all of these oxygens as water. When you use 6 moles of HI would give me 4 hydrogens, which takes out all the oxygen. 3 iodine also goes out, and you still have 2 hydrogens left with. 2 hydrogens are still left with. These two hydrogens would attaches to this carbon because there is already one H, so you would end up getting alkane. And if it had been a case of ketone or aldehyde, then 4 moles of HI are being used. And in 4 moles of HI, 1 water goes out. The 2 hydrogens would take this water out, and 2 hydrogen, whatever is being left, that got attached to this CH, and this also would become alkane, RCH3, along with the loss of 2 moles of iodine. So this is the tip to remember in the case of wherever you want to do the cleavage. So what basically you are being given with, so here you have OH, and here I could see you are being given with COH. So what is the tip to remember? So the tip to remember here is that this entity would require 6 HI, so that I can remove 2 water out and 3 iodine out, and the whatever 2 hydrogens are left, that 2 hydrogens get attached to this part, C, and here I just would attach 2H, and 1 H is already there. Similarly, the same entity would happen in this case also, CH2H, and onto this side, so 6 HI is used here, 6 HI would also be used for this, and what else you are left with, and 2 HI would be used to abstract this water. So the water goes out along with 1 iodine, and this H takes the position of this. So what basically you happen to see here is this H the blue H would come here. Let me show it like this. This H would come here, this H also would come here. So in totality, what I did is that this is COH, this is COH, and this is OH, this is OH. So how many moles of HI are being used? So here you have used 6 HI, 6 HI. Here you have used 2 HI and 2 HI. So in total 6, 6, 12, 12 plus 2 and 2. So 16 HI are being used. And this 16 HI would convert this into this compound, which they have written as 1,2-dimethyl butane. So 16 HI is the Y. This is 16. And this had been 2. So the question would have been in a reverse way. Otherwise, this would not be giving you the right answer. It has to be Y upon X. So this is a mistake happened here. Y upon X. If you would do the Y upon X, then you would get the answer with D. Sometimes these, because this digitization mistake has happened from my side, so it has to be written as, instead of X upon Y, it has to be Y upon X. So then it would give a right answer as 8. So I hope you have enjoyed today's session, because we did lot of problem solving in this particular session. I'm giving you with one homework question. You have to do it and place it onto the comment section. Which among the following anion is a better living room than OH negative? Thanks a lot. If in case you like this particular discussion, do let me know onto the comment section, so that I can place at least 7-8 more sessions of this length for organic, inorganic and physical, so that before your JEE mains or advance you feel strengthened with the topic. Have a nice day, stay safe, take good care of yourself.